whole purpose of computing an LU factorization is to solve a linear system AX equals B. All right? And if we didn't have to do any pivoting, what we then said was, A can be replaced by L times U times X equals B. And then we can say, okay, this is an intermediate vector Z, so we can solve for Z by solving L times Z equals B, and then we can solve for X by solving U times X is equal to Z. Lower triangular solve, upper triangular solve. Okay? Now, what we notice is that if we multiply all of these permutation matrices together, we get another permutation matrix. So if we permute both the right-hand side and the left-hand side by that same permutation matrix, then we can replace P times A by our LU factorization, and we are left with two clean triangular solves, one with the lower triangular matrix, one with the upper triangular matrix. Okay, and on the one hand, this is obviously a very nice, elegant result. And on the other hand, this has some performance benefits because libraries like the basic linear algebra subprograms, which are used to code these kinds of operations, include routines for solving triangular systems, but they don't include routines for interleaving permutation with the application of Gauss transforms. So what this means is that we can ask someone to write a highly optimized implementation of triangular solve, and then we can do the permutation of the right-hand side according to what was encountered during the LU factorization with partial pivoting, and then we're left with most of the computation in two triangular solves. Obviously, permuting a matrix doesn't take as much computation. It's a matter of moving some data around. The real computation then happens in the triangular solves. After, of course, you've done all of the computation required to do the LU factorization.